All righty. So today's lecture is going to be on polarization. We have started talking about light and optics in the previous classes. And we talked about some of the big characteristics, the physical characteristics of light, that being the speed of the wave, the speed of light specifically, and how it relates to the other characteristics, frequency and wavelength. And of course, we had the equation V is equal to F times lambda, which is the general equation for any kind of wave, whether it's light, it's a water wave, a sound wave, it doesn't matter. All waves follow this relationship. But today, we're going to talk about a different physical characteristic about light that's not frequency or wavelength. And as I said, it's called polarization. Now, the thing about polarization is it's not as important of a characteristic to us as frequency, wavelength, and things like that, because our eyes are not made to be able to detect polarization. We can't actually see the polarization of light. If light is polarized in one direction or another direction, we have no idea just by looking at the light. However, it is a detectable thing. It's just our eyes can't detect it. We have to use machines, cameras or other things, or filters. And that allows us to see what the polarization of the light is. But that's not to say just because we can't see it, it's not important at all. It is obviously important. It's a big characteristic about light, a fundamental to it. And there are plenty of things that we make use of which require that light has a polarization. And we'll get to that, of course. Before we do, we need to know what is polarization. What makes light polarized? How do we define that? What is it? Well, if you remember what light is an electromagnetic wave. And so what we said was light, as it moves from, let's say, left to right, will have an electric field which oscillates in one direction. Let's say it's oscillating up and down. So here's the electric field part. And of course, light is flowing to the right. But it also has a second component, which is the magnetic field. And the magnetic field is also oscillating, but the way light is formed, the magnetic field, which is oscillating, is always perpendicular to the electric field. And so what that means is that if, for instance, as I've drawn it here, the electric field is oscillating up and down, then the magnetic field would have to be perpendicular to it. And so let's say it's going back and forward. So it's oscillating like this, let's say, towards you and away from you, towards you and away from you. Okay, such that if that's like the center point, as the wave propagates from left to right, the electric field is oscillating up and down, and a magnetic field, the green wave, is back and forth into the page and out of the page. You can think of it. And that's what light is. And of course, those two fields oscillating are perpendicular to the direction of motion. So there's three perpendicular directions. There's the electric field, the magnetic field, and the direction of motion, all three perpendicular to each other. And that's called a transverse wave. Now, what polarization is it's defined as the direction of oscillation of the electric field. So polarization is the direction of oscillation. Oscillation of what? Because obviously we have two different waves here. We have the electric field waving around and we got the magnetic field waving around. It's defined, it was just chosen because we could choose either one. It was chosen to be the electric field. So in the example I've drawn here, the electric field is oscillating up and down. So we would say this light is polarized upwards or downwards. It doesn't matter, up or down. We would say it's polarized up. And so we can say, okay, this light is polarized upwards. But of course, it doesn't have to be polarized up. That's just how I drew it. Of course, the electric field could be oscillating back and forth, and then the magnetic field is up and down, or left and right, or however we want to do it. As long as they're perpendicular, it doesn't matter. So sometimes the polarization of the electric field can be left to right, up and down, in any direction. It doesn't matter. But whatever direction it is, that's the direction that the light is said to be polarized. And that's it. That's all it is. Light is made up of electric and magnetic fields which are oscillating. They have to oscillate in some direction, and the direction the electric field oscillates is called the polarization. That's all there is to it. Now, because all light is created by electric and magnetic fields oscillating, all light must be polarized, because the electric field has to be oscillating in some direction. And so every light is always polarized in some direction. The thing is, sometimes you will hear that the light from the sun is unpolarized, or light from this particular light bulb is unpolarized. Well, note that unpolarized, quote unquote, all that means is it's randomly polarized. So if we have, let's say, a laser, and the laser is polarized in a certain direction, the light coming out of it is the electric field is always in the same direction, always. But with the sun, we call it unpolarized because all the light that's coming out of the sun, one particle of light may be polarized upwards, the next one may be left to right, the next one may be at a 45-degree angle. Every piece of light that comes out of the sun is just polarized in some random direction. They're not all polarized in the same direction. And so instead of calling it randomly polarized, they call it unpolarized. Okay, so don't let that terminology trick you. There is no light that does not have a polarization. The electric field is oscillating, so there must be a polarization. But sometimes we use the term unpolarized as kind of a shortcut way of saying it's randomly polarized. It's not always in the same direction from this source. Now, why is it important for us to know about polarization if we can't see it? You know, frequency or wavelength is important because we can see it. We see different colors. The reason some things are orange and other things are yellow and other things are blue is because the light that's coming from those things have different frequencies. The higher the frequency, the more blue the color is. The lower the frequency, the more red. And of course, that's just the visible spectrum. We know there's an infinite amount of spectrum out there, and we can only see a very limited amount that we call the visible light. Infrared is out there, microwaves, radio waves, gamma rays. It's all light. And the only thing that makes that light different, an X-ray versus red light, is purely the frequency of the light or the wavelength of the light, whichever way you want to think about it. And so that's why frequency is quite important. But if we can't see polarization, why do we care? Well, the reason is because it actually does make a difference. Just because our eyes can't see it, we can detect the fact that there is polarization and we can make use of it. And one way to do it is this. People have invented pieces of plastic, basically, we call them filters or films, which can block light if it's polarized in a certain direction. Or another way of thinking about it is it allows light through this piece of plastic if the light is polarized in the correct direction. And these are called polarizing filters. Okay. So you can think of it, if you've ever seen the old, what are they called? Transparencies in school, where the teacher, it'd be projected up on the wall and the teacher can write on this clear plastic sheet. Basically a material just, similar to that. And what it does is, if the light is polarized in the same direction as the film, the piece of plastic is created in that same direction, then the light will pass through as if it's completely see-through. It's completely transparent. So if we have light, let's say light is polarized up. That's the way I'm going to show it, by symbols, by arrows. The arrow's direction tells me the direction of polarization. And then we have a filter, piece of plastic. Here it is. And the way I'm going to do this is I'm going to say, okay, this is polarized upwards. And so what happens is, as light, so there may be some light bulb over here on the left, and it's sending light from left to right. And I'm saying the light that's moving from left to right is polarized upwards. Well, when the light hits this piece of plastic, because the plastic is polarized in the upward direction, if the light is also polarized in the upward direction, it can make it through. And so you get all of the light coming through 100% perfect. However, if you have a similar arrangement, but this time the light is polarized to the right, and you have the same filter polarized upwards, then you get nothing coming out. It's completely black. No light gets through. It's blocked. So you get 0% of the light making it through. And of course, if the light is polarized somewhere in between, then you get some light going through, but not all of it. So it darkens the light. It shades it. So because people have invented this type of material, we could do things, very fancy things. One thing I know everybody's familiar with in some way, if you've ever seen it or experienced it, or you've heard of it, is 3D movies. When you go to a movie theater that has 3D movies, you have to wear special either glasses or goggles, depending on what technology they're using. And so what they do is this. When the movie is being created, instead of using a single camera to film the movie, as normally would be done, they want to emulate what our eyes do. Our eyes are separated from each other by a little bit. And so when they see an object, the two eyes are seeing the object from slightly different angles. And that information is being sent to your brain, and your brain, being a really powerful, smart piece of equipment, takes those two images that are slightly off from each other, combines them together to create a three-dimensional image. And so when we look around in our everyday lives, we see the world as three-dimensional. Whereas if you watch TV, the TV screen, of course, is flat. So it's all two-dimensional. So what we'd like to do is be able to emulate this three-dimensional view, so they get two cameras. And the two cameras are separated by a little bit, just like your eyes would be separated. And so both cameras are recording the movie at the same time, but at slightly different angles. And so what they want to do is then, well, look, if we show this movie the way it's filmed, it's blurry, because you have two different images on top of each other that are slightly different. It looks blurry. That's why if you do go to a movie theater that has 3D movies and you don't wear the goggles or the glasses, it looks like a blurry mess. It's horrible. So they need to find a way of tricking your brain into thinking that these two images, which came from two different cameras, but they're put on the same piece of film, are actually coming from your two different eyes. And so if they're coming from your two eyes, then your brain knows how to combine them correctly to make a three-dimensional image. So what they do is first, when they're filming the movie with the two cameras, or let's put it this way, when they project the image in the movie theater, the image from one of the cameras is polarized upwards, and an image from the other camera is polarized to the right. And both images are shown on the screen at once. Your glasses have this kind of material on the lenses, so that, let's say, your left eye can, when it's looking at the screen, only the image that's polarized up can get through. The image that's polarized to the right is blocked. And vice versa with the right eye. The right eye is only seeing the light which is polarized to the right, because the lens on the right side is the opposite polarized lens, and it blocks out the upwards. And so now your left eye is seeing one image without the other, and your right eye is seeing the other image without the first, just as you would in your everyday life when you go look around. Your left eye sees one thing, your right eye sees the other. Your left eye can't see both, it's just one thing. So that tricks your mind, because now one eye sees one image, the other eye sees the other image. They're just a little bit off, just like your eyes are a little bit off. And so your brain configures it and creates a three-dimensional look. And so that's how you get things like 3D movies. Now, this is one technology. There's other ways of doing it. It's what's called active 3D versus passive 3D, all sorts of stuff. But at the basic level, it's all about the polarization. Sending out images that are polarized differently, and then having these filters over your eyes so that one eye sees one thing, the other eye sees the other, and then your brain puts them together for you. Another thing, of course, is sunglasses. Probably where you've heard the term polarized before is when it comes to buying sunglasses, because you could buy polarized sunglasses or unpolarized sunglasses. And so what is that? Well, sunglasses in general, unpolarized, all it is a dark piece of plastic. So you put them on and everything's darker because you've tinted the lens. A polarized sunglasses works differently. They may still tint, or some of them don't tint at all, and they just make use of the polarization. And so what they do is they'll have the lens of the glasses, let's say, polarized upwards, both lenses, only polarized up. And so if you're wearing glasses that are polarized up, when you look out into the real world, the only light that can get to your eyes past the glasses is light that's polarized up. Any light that's polarized to the right is completely blocked and you don't see it. And so that's a way of lowering the amount of light coming into your eyes, dimming it basically, without darkening the image. It just lets less light through, so it's not as bright. And so that's what polarized sunglasses do. And this is good because the light from the sun, as I said, is what's called unpolarized or randomly. So that means half the light coming from the sun is up, the other half is to the right. So when you put on polarized sunglasses, automatically half of all the light coming from the sun is completely blocked. And the other half, of course, is let through because it's polarized in the correct direction. Now, there's lots of other areas polarization is important. You can get into it as you get into physics and engineering. For instance, companies that make sugar syrups and things like this, they found out that when light is sent through a sugar syrup, let's say pancake syrup or corn syrup or something like this, depending on how sugary it is, how sweet it is, the polarizing angle, that is, the light that originally comes into the liquid is up, let's say, Well, as it passes through this sugar syrup, the molecules in the syrup turn the polarized angle so that when it comes out, it's not polarized up anymore. Maybe it's polarized at 30 degrees or 50 degrees. And the more sweet you make the syrup, the more it turns the angle. And so one way these companies test how sweet their syrup is without actually having to go taste it is they send light through. They send light that they know the original polarization is up. They send it through the tank. They receive it at the other end. And then they look, how much did the angle change, the polarization? And then they know a little formula that tells them what the concentration of sugar is, depending on how much the angle changes. They do a little math, and now they know, okay, this is 60% sweet or whatever it is. So that's another way polarization is kind of important. There's lots and lots and lots of places where we use polarization. Even though we can't physically see it with our eyes, it's still useful and we still have to know about it. Now, what are we going to do with polarization? What we're going to do is talk about these polarizing filters and do a little math. For instance, we may want to know if I send light through a polarizer, and maybe I have multiple polarizers. Maybe I have one that's polarized in the upwards direction, and then I have another one after it that's polarized in the 45-degree angle. And I want to know if I send light through, how much light will come out the other side. That's the kind of calculation I want to do. To do this, the law or the equation we're going to use is called the law of Malice. Sounds like a really cool, interesting equation, but it's not malice, M-A-L-I-C-E, like evil. Malice, M-A-L-U-S. It's a guy's name. The law of Malice. And what does it say? What it says is the intensity of light that you get out of the system. So you send light through these polarizers and then you detect it at the end. How much light you detect, the intensity of the light is equal to the intensity you started with. How bright was the light originally before it hit the polarizers, times cosine squared of the angle. Now, what angle are we talking about? This is important. This is the difference between the original polarizing angle and the polarizer or the polarizing film. Okay, so for instance, light's polarized up. So let's say it's at 90 degrees. And we're going to try to get through a polarizer that's polarized at 45 degrees. And I want to know how much light gets through. So we say, okay, the light was originally at 90. We're trying to get through 45. So 90 minus 45, that's the angle we use for this. Okay? And that's it. Very easy. So if we try it, light is polarized up initially. And we're going to try to get through a polarizer that's also polarized up. And I want to know how much light gets through. So we say, okay, whatever the initial intensity is, what we get out, I, is the initial intensity times cosine squared of the initial light is at 90 degrees because it's pointing straight up, and the polarizer is at 90 degrees. So the angle is the original 90 minus the filter 90, which is 0 degrees. And so we put this in our calculator, cosine squared of 0, that's cosine of 0 times cosine of 0, which is 1 times 1 is 1. So we just get whatever the initial intensity was. Or in other words, 100%, all of the light, one or 100% gets through. However, if we have light that's polarized up and we're trying to get through a polarizer that's polarized horizontally, what light gets through? Oh, same thing. I is whatever we start with, I naught times cosine squared of, well, the initial light is at 90. The polarizer is horizontal, so that's 0 degrees. So the angle I put is 90 minus 0, which is 90. So again, put it in my calculator. Cosine of 90 times cosine of 90 is 0 times 0. We get no light coming through, which makes sense. The polarizer is polarized to the right. The light is polarized up. They're in opposite directions. They're perpendicular. So none of the light can get through. It's all blocked. Now, what starts to get a little more interesting is when we have light polarized up, and now we try to get through a polarizer that's polarized at an angle. And the way I show it is I do this little symbol, a dotted line horizontal, and then the arrow is kind of at an angle. And I'll put the angle here, 30 degrees. This is the symbology I'm going to use for our problems. And I say, okay, how much light gets through? Well, we're going to do the same thing. I is I naught, whatever we start with, times cosine squared of the angle. What's the angle? Well, the light starts at 90 because it's upwards. We're trying to get through 30. So 90 minus 30 is 60 degrees. Okay, so notice I'm not putting cosine squared of 30. 30 is the angle of the polarizer, which is fine. But the angle in the equation is not what does the polarizer say, it's the difference. I'm coming in with an angle, the polarizer is at an angle, the difference between those two angles is what goes here. So I'm coming in with 90, I'm trying to get through a 30, so 90 minus 30 is 60. So I put this in my calculator. Cosine squared of 60 is 0.25. So the answer is 0.25 times I naught. Or 1/4 of the light makes it through. 1/4 of the light. Now this is a big important example because it's very easy to make the mistake when you go to plug in your angle to just plug this number in. That's not the number you use. You need that number to get the correct answer. But remember, the angle in the law of Malice is not the angle of the polarizer, and it's not the angle of the light. It's the difference between them. I came in with one angle. I'm trying to get through something that's at a different angle. So I subtract those two numbers together, and I get the angle that I plug into the law of Malice. Now, this is all good. Let's say we're getting it. This is fine. But what about something a little more interesting? What if I have multiple polarizing filters? Instead of just one thing, what if I try to get through a series, 2 or 3 different filters? And I want to know, what do I get at the end? How do I use the law of Malice now? Well, it turns out it's very easy. All I have to do is multiply onto this law of Malice equation more and more cosine squareds. Each filter will give me a cosine squared. So if I have 2 filters, let's say here's my example. Light is polarized up. I try to get through an upwards, and then I try to get through a horizontal. Okay. And I want to know, what do I get here? Well, the way we're going to think about it is this. First, the light has to go through the first filter. Some amount of the light is going to get through. How much? Well, the amount that gets through the first one is I naught cosine squared of theta. Let's say theta 1. And so now once that's happened, what's left is now light that's polarized in whatever direction this first filter is. Okay, so for this one, the filter is polarized up. So only light that's polarized up is going to make it through. So now some amount of light has made it through, whatever this number is. And I know its direction is this direction. Now that thing has to get through the next filter. So this thing now has to hit another cosine squared, this time theta 2. Because this light now has to get through that filter. And so for every filter, you're just going to multiply on another cosine squared. So let's try it with this one. What do we have? The amount of light that gets through is I naught, whatever we start with, times the first one. I'm at 90, and I'm trying to get through 90. So I have cosine squared of 90 minus 90, which is 0. Then what's happened? I've gotten through whatever I've gotten through, whatever this number happens to be, that's what got through. And I know the direction that got through. The direction of the light that got through is whatever the direction of this filter is. Forget about the initial light. The initial light is gone. What you have now is what made it through. And what made it through is always the same direction as the filter it went through. Now, in this example, it happens to be the same direction, but that's just because of the numbers I chose. But if this first filter were at 60 degrees, then the light that got through is at 60 degrees now. It's not at 90 anymore. But anyway, okay, so now we have the light got through the first guy. Now it has to get through the second. So cosine squared of what? This light and this filter. Well, this light is 90. This filter is 0. So I'm at 90, trying to get through 0. 90 minus 0 is 90. And there we go. Exactly like the first examples where you only have one filter, I naught times cosine squared of whatever the angle is. With two filters, I naught times cosine squared of the first one, then times cosine squared of the next one. And if I had a third filter, cosine squared of the third one. And you just keep building up cosine squareds and you multiply. You don't add them. You multiply these cosines. So if I do this or plug it in my calculator, I find out the answer is 0. No light gets through for this example. Well, let's try another. Let's say light is polarized up. I try to get through something that's polarized at, let's say, 30 degrees. Then I try to get through something that's polarized horizontally. There's my example now. All right, so how much light comes out? Well, I is I naught, whatever I start with. Now, in a real life thing, you'd know this number I naught. It's some intensity. For us, we don't need to know what this number is. So I'm just always going to leave it as I naught. I'm never going to give you a number for I naught. It's just a variable. Leave it as I naught. But if you're working in a factory or you're doing some theoretical work, then you need to know, oh, it's 4.5 times 10 to the 6th is the intensity. And so you just plug a number in there. But we're just going to leave it as I naught every single time. So don't worry about whatever that number is. So light, I start at 90 degrees and I'm trying to get through 30 degrees. So I have cosine squared of 90 minus 30, which is 60. And now what? I've now gone through the first filter Whatever's left is light. And which direction is this light polarized? It's polarized in whatever this angle is, 30 degrees. So now my light is sitting there at 30 degrees, and I want to get through the next filter. So I have another cosine. Cosine squared of what? I'm at 30, and I'm trying to get through 0. 30 minus 0 is 30. And there we go. Now I stick this in my calculator. I have cosine 60 times cosine 30, and I square this thing, and I get 0.1875 I naught. That's how much. About 20%. 0.18 is 18%. About 20% of the light will make it through this set of polarizers. But whatever, that's the number. So notice, when I add more filters, I'm just going to multiply more cosines. Also notice, when light makes it through the first filter, this new light is no longer at the same angle as the original. It's now some new angle. What angle is it? Whatever the filter was, that's the angle of the new light. And now that new light has to make it through the next filter. And of course, once it makes it through there, this light now is polarized in the direction of the new filter, in this case, 0 degrees horizontally. And so on. I could have 3 filters, 4 filters, however many I want. All I would do is multiply on more cosines. Now, the last little thing I want to do, of course, this is kind of the theory thing. We're going to do more examples later. The last thing I want to tell you, just as a shortcut, is anytime you're doing a problem like this, and you see one right after the other, 2 things that are perpendicular, for instance, right here, you have upwards polarized going to horizontal polarized with nothing in between, you always get 0. Here it is again, right here. You start upwards and you're trying to get through horizontal. There's nothing in between. They're perpendicular. You get the answer 0. If light is polarized perpendicular to the filter, or the filter is perpendicular to the light, it's always 0. All of it's blocked. But notice here. Here we have up. Here we have horizontal. They're perpendicular. But this time there's something in between. There's a filter there. The presence of that filter makes it so that you can't just assume it's 0 anymore. That filter changes the light in some way. And that's why this answer is not 0, it's something. Which you may not think that's weird. You just say, okay, whatever. This is very weird. Because think about what this is saying. In this example right here, this circled red one, light is polarized up, and we're trying to get through horizontal, and that horizontal guy blocks it all. No light can make it through this system. So it's like it's completely opaque. It's a wall. You can't make it through. However, just by inserting something in the middle, this thing right here, and all that thing does is block light. It doesn't add light to anything. It blocks light. Somehow inserting something that blocks even more light, all of a sudden now we get light coming out. You started, no light can make it through. You put something in between that blocks light, and now light can make it through. That's a very, very weird thing. Because like I said, if you think about it, pretend you're sitting there in your room, you look at the wall of your room and you have a flashlight. You shine a flashlight at your wall, and someone in the other room So, the light is blocked. They don't see the light coming through the wall, obviously. But then if you put this piece of paper between your flashlight and the wall, now all of a sudden light gets through the wall. That's basically what's happening here. So it's a very, very weird thing. And what it tells us is what's happening is not straightforward. What we may think is, oh, the polarizer is like it's a piece of plastic that has slits, long holes. And so if it's like a slit, here's our polarizer, and there's a bunch of slits, openings like this, vertical. And so if light is upwards, then that light can fit through these slits. Because it's upwards, the holes are upwards, it fits through. But if you have light that's horizontal, well, it can't fit through this slit because it's too wide. Only light that's polarized up can get through because the holes are up, but these things that are sideways can't fit through these holes. That's a way we like to think about what's going on, but this example about sticking this extra filter in the middle, now light can get through, shows us this is not the right picture. There's something else happening at the quantum level, the microscopic level. And so as you progress into these fields, you start to learn about the quantum nature of light and some of the weird aspects. But for now, it's just interesting to note that this thing is true. Here's something that blocks all the light. You stick another something in between, and now all of a sudden light is getting through. It's just a weird thing to think about. Anyway, that's polarization. This is what we're going to be doing. This part of optics, we're going to concentrate on the law of Malice. So next class, we'll go ahead and work some more examples, make sure we understand how to do these calculations, and go from there. So I hope this was understandable, and until next time, I will see you later.